Okay, let's talk about the quantum mechanical picture of the atom. We alluded to that a little bit last time with the Broglie wavelength. If it has a wavelength, then the particle properties aren't completely apparent, and it's more going to be more proper to talk about it as a probability function. Werner Heisenberg introduced the concept and the uncertainty principle, and he said that it was impossible to know the exact position, the exact momentum of an electron or any other small particle at the same time. There'd be a bit of an error or uncertainty in that. And that's because detecting the electron with, say, light of some sort of electromagnetic radiation displaces the electron a little bit, so we're not quite sure. There's a little bit of a margin of error. Electron microscope uses that sort of phenomenon. You can see things, but they're a little bit fuzzy because of that uncertainty. Um, Consequently, we can't speak about the electron's exact position or momentum, or its velocity for that matter, but we talk about where it is in terms of a probability function. And these probability functions are called orbitals in quantum mechanics, and they describe a three-dimensional region of space in which the electron has a 90 to 95% probability of being found. Now, is that completely unlike a probability function, say, in your stats course? Not really, but these functions are certainly more complicated. So much that at this level, we're really not going to talk about them in great detail. If you take a higher level course in this introductory level course, they will talk about it if you take physical chemistry or something like that. So let's talk about the basic ideas. Atoms or molecules can exist in certain energy states. Each energy state of the atom or molecule has a definite energy. When the molecule changes energy state, it must emit or absorb just enough energy to bring it to the new energy state or quantum condition. That sounds a lot like Bohr's model of the atom, which we did in the previous presentation. And the second one's pretty similar too. Atoms or molecules emit or absorb radiation or light as they change their energies. That light may or may not be visible. But hey, that's pretty much what Bohr said too. But it turns out it needs to be more sophisticated than what Bohr said. Bohr only had one quantum number, the n, but the allowed energy states in an atom or molecule can be described by sets of numbers called quantum numbers. In modern quantum mechanics, according to the quantum solutions by Schrödinger, Heisenberg, and Dirac's equations, but when Schrödinger solved the hydrogen atom in the 1950s, he had 4 different quantum numbers. And this is a simplified version of that equation. Schrödinger's equation is a function that's displayed as follows. You see the h with a little hat times the Greek letter psi equals the energy of the system times the psi again. Now the E is the total energy of the system. H with the little hat, when you see a variable with a hat, that means it's an operator. That means instead of representing just a number, it represents a mathematical function. And the Hamiltonian operator is a function of the kinetic and potential energies, where the psi is the wave function. Now, the wave function is our probability function, and it describes where the electron is likely to be found. And again, that's about a 90 to 95% probability based on that probability function and the definition of those 4 quantum numbers. So we say that orbital is represented by 4 quantum numbers, the n, the L, the m sub L, and the m sub S. We represent the L as sort of a little cursive letter L. That way it's indistinguishable from a 1. So if we just drew a lowercase l, it'd look too much like a 1 in some cases and cause confusion. So let's look at the principal quantum number n. It's similar in meaning to the n in Bohr's model, but just like in Bohr's model, n could be 1, 2, 3, 4. That's the shell. Sometimes the n could be k, l, m, and n shells, but we're not going to mess with that too much for this course. We'll save that for a more advanced course than this. So that's pretty straightforward. Now, the L is the angular momentum quantum number. And it's that scripted looking L. Now, L can be 0, 1, 2, 3, 4, 5, etc., all the way up to 1 less than the value of the current N. That is the current number of the shell we're in. So certain L's won't be allowed. Now, we often give those letter designations. So L equals 0 is an S, 1's a P, 2's a D, 3's an F. And that's as far as we'll really go with it in this class. But you could theoretically go G, H, in alphabetical order after F after that. L tells us the shape and the kind of orbital we're talking about. We use those letter designations in combination with the number of N and the letter for L, we can designate which orbital in which shell it is we're talking about. For example, let's look at these. So if we got N is 1 and L is 0, so we're going to indicate the 1 for the value of N. Now L equals 0 is an S, so N is 1 and L is 0 represents a 1s orbital. If N is 2 and L is 1, so we're going to write the 2 for the N. L equals 1 is a p orbital, so we're talking about a 2p orbital. Now if N is 3, we're going to write the 3. L equals 2 equals a d orbital, so I'm referring to a 3d orbital. But certain combinations are not going to be allowed. That is, there's no p orbital on the first row, because if N is 1, L can only be equal to 0. And so a 1p or a 2d are not going to be allowed based on the value of L. And that brings us to the next question, which of the following is not allowed? All right, S is allowed for all, but that 1p is not an allowed orbital because you only get an S orbital. Now 3d, the d's actually start with 3. L equals 2 is d, so you're going to see that starting on the third row. 5F is certainly allowed. F's start with 4. So S's start with 1, P's start with 2, D's start with 3, and the F's will actually start with 4. Any number less than that's not going to be an allowed orbital. Let's look at the magnetic quantum number. Now, the symbol for the magnetic quantum number is m sub L. And it tells us how that orbital is arranged in three-dimensional space. It also tells us how many orbitals there are of that type per value of n. M sub L ranges from negative L to positive L, including 0. So if we look at it, for L equals 0, which represents an s orbital, M sub L can only be 0, which means there's only one value of M sub L, which implies that there's one s orbital per value of n greater than or equal to 1. For L equals 1, we can see that that's a p orbital, and then the values are negative 1, 0, and positive 1. That means there's 3 values of M sub L, meaning that there are 3 p orbitals per value of n greater than or equal to 2. L equals 2 is a d orbital, and that means M sub L can be negative 2, negative 1, 0, plus 1, plus 2. It means there are 5 values of M sub L for n's greater than or equal to 3. If L is equal to 3, then that's an F orbital, then M sub L is negative 3, negative 2, negative 1, 0, plus 1, plus 2, plus 3, which means there are 7 values of M sub L, which means there are 7 F orbitals per value of n greater than or equal to 4. Theoretically, we could keep going with more orbitals, but practically speaking, we're just going to look at the ground level electron configurations, which only involves sp, d, and f. So s orbitals tend to be spherically symmetric, but they get bigger per value of n. Be familiar with the shape of the orbitals. Be able to pick them out of a lineup, I would say. P orbitals, they say they are kind of dumbbell shape, but me they almost look like a figure 8 or more like a peanut or something. But there's a node in the middle, meaning an area of 0 probability. Remember Heisenberg's uncertainty principles in effect, so it's not truly 0, but they're oriented along the x, y, and z axes. So you got a px, a py, and a pz. 3 different p orbitals per value of n. D orbitals have a little bit more complex shapes and complex names, but most of them look kind of like a 4-leaf clover, oriented differently in 3-dimensional space, where the dz squared looks like a p orbital with a donut around it. The f orbitals have more complex shapes with 6 lobes, where one of the f orbitals, it looks like a p orbital with 2 donuts. So those are your f orbitals. Again, it's not art class, but I'd be able to pick the orbital out of a lineup. The magnetic spin quantum number tells us the magnetic spin. That is, if I've got 2 electrons in the same orbital, they have to have opposing spin. So m sub s can be plus 1/2 or minus 1/2. Wolfgang Pauli, 1925, came up with the exclusion principle, which essentially stated that in an atom, no electron could have the exact same 4 quantum numbers. Since we're talking about a probability function involved, the numbers are the same. You got 2 objects occupying the same space under the same conditions, which would mean they're the same electron. But opposing the spin allows 2 electrons to occupy 1 orbital at one time. And it distinguishes between the two. So 2 electrons per orbital. That's the consequence of Pauli's exclusion principle. Now, 2 electrons are designated as one having spin up, one having spin down. We indicate that with an upward pointing arrow and a downward pointing arrow when we end up drawing our orbital diagrams. The spin describes the electron's magnetic fields. Unpaired electrons, you'd have either they would be up or down, but they wouldn't be paired together. If you have unpaired spins, we say that is paramagnetic. Paramagnetic atoms are attracted to a magnet. There's a special case of that called ferromagnetic with like iron or cobalt or nickel, which we use to make permanent magnets, where that alignment of the electron spins with the magnetic field lasts a much longer time, generating a permanent magnet, but only certain elements will retain that. Usually the spins will go back to being random after the magnetic field is turned off. If the spins are paired, then we put them together, one up, one down. By convention, we tend to put the positive spin in first, although there's really no rule that says the first electron has to have a positive spin. It could technically be either one. But if they're all paired up and there's no unpaired electrons, we'd say that is diamagnetic, and those are repelled by the magnet. So let's look at some questions there. So see that we remember everything. So L equals 1 represents a p orbital. If I got what values of L are allowed for n equals 3? Remember, L can range from 0 to n minus 1. So the values of L would be 0, 1, and 2, but not 3. It's not allowed. So that corresponds to, for L equals 3, I could get an S, a P, or a D orbital with n equals 3. What are the values of m sub L for L equals 2? So it's going to be -2, -1, 0, +1, and +2. Ranges -L to +L, including 0. And so we'll pick back up and apply some of this when we talk about electron configurations next time.